Okay, so my name is Éric Grégoire. My co-author Jean-Marie Lagniez is also there, so he will be happy to answer your questions too. And we are all coming from France, another part of France, and the title of this talk is a general AI approach for skeptical reasoning. I guess that at this point you are thinking, wow, this French guy is always making a mistake in the title because he's talking about general AI and not artificial general intelligence. Well, I did it on purpose because I think that the kind of reasoning paradigm that we are studying do not belong to general intelligence. Actually, it relies on general intelligence, but requires more. As an old professor, I know that most students do not have the basic capacities in logical things, and so it's the reason why I prefer talking about general AI approach than artificial general intelligence approach. So this talk is about the way to implement a form of reasoning that is general, that is not domain dependent, and that we believe that must belong to a form of advanced reasoning. And this pattern of reasoning is simply how to behave in front of conflicting information that are not obvious, that is not obvious, or to obey a policy to handle this conflicting information in a rational way. Okay? More precisely, this paper is about the way to handle inconsistent knowledge. By inconsistent, I mean that we have some symbolic information that is unsatisfiable. I associate a notion of truth or truth value to this formalism, and I consider not only logic-based formalism, but actually any representation formalism where you have inconsistency notion and a compactness theory about this inconsistency notion, and when this inconsistency notion can be solved in a finite time. A straightforward example is about Boolean logic or other logic, and handling contradictory knowledge in a correct way is a ubiquitous issue, a very important issue. For example, if you are smart, if you are a smart logician, you will be able to infer any information and its contrary in front of any single piece of contradictory information. So if you have a huge knowledge set, and if you have any small contradictory information inside, then your whole reasoning will collapse. So it is very important, obviously, to be able to extract those information. This is part of intelligence, and to reason despite this kind of contradiction. This pattern of reasoning does not only belong to logic. For example, if you have, as it is common in AI, some goal to reach, and you have expressed a problem as a set of specifications, and when your specifications contain some contradictions, making the whole problem without any global solution. Or can you behave intelligently in front of this? You are going to try to find out the contradictory information and get rid of them. But there are several ways to do that. And so this is the goal of this paper, to describe a policy about that. So we have some basic paradigms that we should be able to implement. The first one is to be able to extract, to recognize what is conflicting. Okay? And when you have recognized what is conflicting, what are you going to do with this? And in this way, we see some usual approaches in AI that range from credulous to skeptical reasoning when you have several, when you have conflicting information, two pieces of conflicting information. Either you adopt one of them, giving rise to some credulous reasoning, one possible path of reasoning is conflicting with another possible one, or at the other extreme, you adopt what is called a skeptical reasoning, in which you will be very careful. you only take as a conclusion what does belong to any conflicting part of the knowledge. So if because of conflicting information you have incompatible reasoning parts, you will be only able to infer what is common, what is shared by all those parts. And we believe that this is a very important pattern of reasoning, of intelligence, but it is very hard to compute. And so our idea is to refine these approaches from credulous to skeptical reasoning, depending on two things. The first thing is depending on the available computing resource. And the second thing is according to the way human will behave in front of this conflicting information. So we, as I just said, we mimic common human abilities, at least we believe that these are human abilities that are common, and improve computational variability at the same time. And also we study some assumptions about the topology of conflicting information, and more importantly, about the way humans, normal humans, or say normal students, will behave in front of this conflicting information. And all this gives us a progressive range of reasoning paradigms that depend on the remaining available computing resources. There are some small technicalities inside the paper, so I will skip them. I will just try to give you a feeling of what is done technically. We have instantiated this approach to the Boolean case, Boolean logic case. Okay? And in Boolean logic, obviously, you have several formulas, that can conflict, that are inconsistent one another. And in order to recognize the minimal conflicting information, we use, let's say, I don't have pointer, sorry, a definition tree, which is called a muse, a minimal set of conflicting information. If you extract some information from this, this will not be conflicting anymore. This is the basic thing about conflict, logical conflict in Boolean logic. And there are other dual concepts that are working with that. This is maximal satisfiable subset. You cannot add more information without giving rise to inconsistency. And the complement of this is called co-immensets. And these are the only three basic concepts that we require at this time. Well, let us go back to credulous and skeptical reasoning. Credulous reasoning is the same as trying to find an MSS, maximal satisfiable subset of the theory. Okay? Skeptical reasoning consists in computing all minimal unsatisfiable subsets in order to get rid of the information that belong to at least one of those minimal unsatisfiable subsets. This explains why those things are very high in the complexity scale. The last sentence says that there can be an exponential number of causes of inconsistency in a single theory, making the whole thing totally intractable. So in AI, generally, when people talk about skeptical reasoning, they say, oh, it's high in the polynomial hierarchy. It can even be exponential, actually. So we don't treat that. Our goal is, however, to try to treat them despite this complexity. On the other hand, when you have credulous reasoning, it's also an NP-hard problem. So it's not so easy to compute, to extract the conflicting information and to get rid of it. This is very high in the polynomial hierarchy for some of the problem. So we have devised a progressive architecture to handle this problem of having conflicting information in Boolean theories. The first approach is very easy, is to try to show that the theory is unsatisfiable. and there's been a huge progress in satisfiability practical checking this last year. We call this full attitude because we stop when we have a single maximal consistent subset. This means that we have one single possible way to have maximal non-conflicting information in the theory. And for this, but I will skip the technical details, we use some very nice features of set solvers that deliver us what we need actually. This is called the interpretation, the progressive interpretation. This is called the full attitude. The credulous reasoning is to make sure that the non-conflicting information that we get is maximal, that we did not reject too much things. Okay? And for this, we use very efficient tools, despite the problems NP hard. We have presented this this week at AAA High. And for ideal skepticism, we cannot solve this because this is totally intractable. But we have devised a full range of techniques to address, to some extent, this skeptical reasoning thing according to what humans are doing. Just to give you a few examples, because time is running out very fast, you can decide to look for contradictions that involve a small number of formulas. Okay? Perhaps you will miss some reasons for inconsistencies, this is assumption 1, but you will be as smart as humans that can find contradictions that involve no more than k formulas or clauses also. And there are other assumptions that we can devise that all make use of parameters that we can increase depending on the available computing time. I will skip all of this, but this explains also that causes of inconsistency can intersect, and so there are many ways to handle them in an intelligent way. And since I have almost no time now, just to show that it works. So we decided to check all this theory on difficult problems. More precisely, we took benchmarks from competitions that are expectedly very hard for column-assessed and use computation. So these are not basic set of formulas. They are very hard to solve, not only to show satisfiability or unsatisfiability, but also to find reasons for unsatisfiability. Okay? And we have applied successively a series of progressive reasoning that I've just described, either the full attitude, which we were able to solve almost all problems in less than 1 second, the credulous attitude, which tries to find out one maximal consistent subset, also solve almost all problems in less than 1 second, very easy. Now the ideal skepticism is intractable. For almost all problems, we were unable to find a solution. This is exponential, okay? And we have devised techniques to find out independent nuances, or, but I don't have time to explain it, more intelligent way to progressively reach the ideal skepticism. Just to show you some kind of results, you have the name of benchmark. The second column gives you the number of Boolean variables, and the third one, the number of formulas or clauses. As you can see, these are not very small ones, and they are very hard they are not simply, they are very hard for muse finding. In the first result column, we have the time for the full attitude, for the credulous attitude. We almost solved all of them. For ideal skepticism, we could not reach the result most of the time. And for the other approach that I do not have time to present, unfortunately, we were able to find the reasons for inconsistency. And the number of clauses that are over here and over here describe the minimal number of clauses that are required to prove inconsistency. showing you when you have more than, I don't know, more than 1,000 clauses, you really need to inspect all those clauses in order to find a proof of consistency. This is not basic intelligence. It's very hard for humans to do. It's impossible for humans to do. But we managed to solve it, despite the fact that for ideal skepticism, for computing all noises, this is intractable. So, just to conclude, the aim of our work is to revisit some basic reasoning paradigms in AI that were supposed to be very complex, very hard to solve. They were very hard to solve because they take the worst case scenario and they do not take into account the way humans are going to try to solve them. Obviously, we cannot reach the worst case, but in most situations, we have some solutions that are as smart as what people would do in this case. So the architecture is anytime to handle contradictory knowledge. Although we have implemented it to logic, it can be extended quite easily to, for instance, CSP, constraint solving program, in the final case. All we need is a compactness result about consistency. This consistency thing should be finite. The architecture proved experimentally efficient, even for those hard problems. We think that it is more close to the way humans would solve this problem if they were asked to solve that. Okay, thank you.